Yeah, thanks very much. Thanks to the organisers for having us here. Yeah, a bit of a change of topic. So I'm going to be talking about joint work with Johannes Kleiner, looking at a theory of consciousness called integrated information theory, and how we can study this thing categorically. So while the study may have been somewhat on the fringes of science, maybe over a lot of the 20th century, recently there's been, I'd say, quite a bit of new interest in trying to study consciousness scientifically, mainly coming from neuroscience. And there's been a few different theories that have emerged. They all kind of address different questions, but if we think about the one we're talking about today, which would be IoT, it's sort of thinking about questions such as these. So we want to know which systems do exhibit some sort of consciousness, by which I mean sort of conscious experience, subjective experience. And if so, how much do they exhibit? So we can imagine that consciousness happens on some scale. And maybe these theories might even attempt to answer something about what that conscious experience is like, so what they're conscious of. This talk's going to be about a theory called integrated information theory. And the reason for talking about this one is that it's perhaps the most formal of these theories that are out at the moment. So it's quite useful just as a template for thinking about them. And in particular, we can see it can be given a sort of semantics feel. But even if you find some of these connections with consciousness sort of highly debatable, which would be reasonable, hopefully the theory is of some interest anyway, because essentially what it boils down to is this toolkit for studying systems and talking about how integrated they are, particularly in terms of their causal relationships. And you might think that thinking about how integrated systems are is interesting anyway, like they might be more efficient or something like that. So people have applied this toolkit to a range of other settings outside of consciousness. I'll now try and give a 2-slide summary of the theory, but then we'll talk about it more as the talk goes on. So it's due to Giulio Tononi, and it's become quite a big project around his lab, developing this theory at IIT. It basically starts from a lot of supposedly quite evident axioms given by reflecting on what conscious experience is like, and then it tries to think about what kind of systems could produce this kind of behavior, essentially. And it ends up with its claim for an algorithm where you give it a system and you give it what state the system's in, such as a brain, but it could be anything. And then it produces a load of stuff. So 2 things it produces, the main ones are, the most famous is this number called phi, which is supposed to tell you how conscious the system would be when it's in that state. And as well as that, it also gives you a mathematical object that's supposed to describe something about the nature of the experience the system would be having in that state. And probably the central one of these axioms that the theory is about is that experience, if we think about experience, is that it's supposed to be an integrated thing. This is the claim. So when you're having experience of being in a room, it's not just a load of sub-experiences of this bookcase over here and the chair or whatever. They all sort of come together into one thing that we think of as the experience. So the theory thinks that this level of integration is what's important. So in particular, this quantity phi that it uses to talk about how conscious something is comes down to looking at the causal relations of your system and seeing how integrated they are. And I'll attempt to now summarize how it does that, but this will have to be a bit hand-wavy. So there's been a few different versions of the theory that have been introduced, and it's currently up to one called IIT 3.0. So in this version, you give your system basically as a set of nodes. I'll probably say a lot, but I think they're called elements officially. And they all have their state space each. Most of the time, they just take the state space to be 0 or 1. So you're basically thinking of them as like neurons, and they can either fire, so they'd be on, or they'd be off. And then you give it a time evolution, which can be probabilistic. So if you tell it a current state, i.e. you give it a state for each element, it tells you the probabilities of it evolving in one sort of time step to being in some other state. So if we just skip down to the picture here, I've attempted to draw all of that in one picture. These are the kind of diagrams that appear in the IIT papers. So here there's just 3 elements, so 3 nodes, and that green is meant to be on and red off, let's say. And then we've also tried to draw the time evolution as well. So on each node, we've written what the node would be in the next time step as a function of the other 2 nodes in the previous time step. That's just how this system would happen to work. So often you see these sorts of diagrams in the IIT papers. So that would be the system S. Now, well, just as an example, then take the top node OR, right? So it would be if the bottom nodes are on or off, it would do the Boolean OR of them to determine whether it's on in the next time step. And when you've got this system now with this evolution, you can basically get a load of different probability distributions that are called the cause-effect repertoire. they're supposed to capture the causal relationships of your system. So what they are specifically is you take two subsystems of your system, one called the mechanism M and one called the purview P, and you're just thinking about how knowing something about the one constrains what you know about the other. So basically you say, oh, if I know the state of M, such as these two nodes on the left, what are the probabilities for all the different states P could be in the previous time step, and that's called the cause repertoire, or in the next time step, and that's called the effect repertoire. So that gives you probability distribution of all the different states P could be in. So you basically have this big bag of loads of distributions, and you want to talk about how integrated they are. And what that means is, okay, you think about all the ways you could divide up your system instead. So if you imagine that you had the same system, but you do what you call cutting it, where you change the time evolution so that some parts of the system don't interact anymore. So here we've basically cut out, on the right, we've cut out the bottom right node. We've cut that away from everything else. So that means all the causal connections between that node and everything else have been replaced by noise. So like you'd plug in mixed random states into your evolution. And that's not exactly how it works in IoT 3.0, but that's a rough picture to have in your mind. Okay, so then imagine, okay, what if instead of my system I had this other system where it had been cut up in this way? How much does this change the repertoires? So you basically end up giving a number for each one of these distributions as to how integrated it is by seeing how much it differs from all these ways that you can cut it up. And then you put a load of these most integrated ones, these most integrated repertoires together into something that's supposed to describe the experience of the system as a whole. And in particular, this thing ends up with a intensity, which is this big phi, which is sort of comes from how integrated the whole thing is as well. So we don't need to know exactly the details of this algorithm. We'll just need to think about what we're really seeing in these pictures. And that is, we need to be able to talk about systems, we need to talk about subsystems of them, and we need to talk about sort of cutting them up to affect the time evolution between parts of them. So anyway, this is what IoT 3.0 is like, roughly. It has a couple of limitations. So it's often just defined for lots of examples and not completely formally, although there is a Python implementation. So you can find ultimately a formal definition of the theory. Perhaps more significantly, it only applies to these quite toy kind of systems I just described there, which are very classical. But if it's meant to be a fundamental theory about consciousness, which is what it claims to be, then it should be applicable to basically any physical system, so maybe quantum ones, for example. So what we've done in these two papers with Johannes and myself is try and formalize the theory. So that's what we did in the first paper on the left. So we formalized it, and once we've done so, it's kind of easy to generalize it now, where you can replace the classical physics parts with other physics. And in this work, it's a paper that goes along with that, where we're studying what we ended up with in that formalization, which is what we call a generalized IoT. So it's like IoT 3.0 would be a special case, and now we have more general versions of the theory. And now we're talking about how those can be studied categorically. So we don't need to know exactly what a generalized IoT is. We'll sort of define it as we go. But it's basically about saying how all these notions from IoT are quite natural to study with diagrams in process theories. And surprisingly for us, this work got picked up as a cover story, essentially, in New Scientist with a suitably provocative headline. You can see there. Okay, so the plan is to talk about IoT using these process theories, which I'll have to now quickly introduce. Mathematically, I'm talking about a symmetric monodal category whenever I say process theory. So I'm hoping a lot of people have seen these before. You don't have to worry too much about the mathematics, really just the diagrams here. So the processes I'm drawing from bottom to top. So a process from A to B is going to look like a box with a wire for A and a wire for B, with the input at the bottom. And what you can do then is plug these boxes together to build more general processes. You can also plug the objects, so the types of the processes, together with this tensor operation. So here we're tensoring things on the bottom right, and on the left we're just doing the sequential composition of processes. And that just means we're working in one of these monoidal categories. And so basically you can end up drawing more general diagrams where you've plugged things together. And I'll also talk about states, which are processes with no input, like this state row here. But basically we'll just be using diagrams where we think of them as like boxes of processes. Here we'll also need some other things that give our processes a bit of an operational feeling to them. So it's known that if you want to talk about causal relationships, you can do so in process theories which have these features. So every object we're going to assume has a special process that lets you throw it away or discard it, or you can think of it as just ignoring it, and that's this ground symbol on the left. And we'll also have the sort of opposite thing where you can prepare your system, sorry, in a completely random state. This is like a maximally random state of your object, and that's the upside down ground symbol. And a few people, including Bob, have worked on how these relate to causality. Here I'll just have to say that we'll call something causal when it preserves this discarding process. That's what we call a causal process. The final thing we need is when you're doing this IoT algorithm, you have to talk about distances between these distributions, like I mentioned. So to do those distances, you need something like a metric, but we won't assume that it's a full metric. But we just want that whenever we have two causal states of some object, we want to be able to talk about how close they are to each other. So we need some notion of distance in our process theory. That's the sort of background setting that we're working on then. And then we'll talk about how we can do IoT in this kind of a theory. Examples of such things. So the one that classical IoT will use, so IoT 3.0, is classical physics, basically. So the objects here would basically be sets, but they need to have this metric. So they're finite metric spaces. And the processes between them are essentially probabilistic maps. So you send each element of your first object to a distribution over elements of the other one. Those would be your processes, but the distributions just don't have to be normalized. And then the tensor would just be sort of taking products of sets. And so this discarding thing corresponds to taking marginals in probability theory. And the causal states really would just be probability distributions. So that's the key idea. So a causal state in this theory of an object is just a distribution over it, all these elements of it. And you can give these a metric when you've got one on the object to begin with. The other one would be quantum theory for those who are familiar with it. So there you can work with finite dimensional Hilbert spaces and completely positive maps between them. And then the symbols correspond to what you'd expect. So you have the tensor product, and the analog to marginalizing in quantum theory is taking partial traces. And your states are now quantum states, which are density matrices. So maybe this top one class is the one we'll mainly have in mind as we go. So now let's try and talk about some of the things that came into that definition of IoT using this process theoretic language. And the main idea was integration, right? So we want to be able to talk about how integrated something is. To do that, we basically want to compare it against ways it could be decomposed. So I think the central sort of basic process theory definition that comes out of this work is the following. And it's just that we are thinking about decompositions of an object. So if we're in one of these process theories, a decomposition of this object S would be a pair of objects, A and A dash, and some isomorphism of that object as a tensor of those two things. So basically, we're just saying it's a way of viewing S as made up of A and some other stuff A dash. So it's a way of dividing up your object. And in pictures, we'll draw these with like a triangle. So the isomorphism is the triangle and its inverse is the upside down triangle. So the fact that it's an isomorphism, I didn't define that, but it just means that you'd have these diagrams at the bottom. So you plug the triangles together and it leaves your system alone. That's what we mean by this blank wire at the bottom. Or you plug them the other way and that would leave A and A dash alone. So it means that we can just view S as being this pair of objects. Now we can talk about generalized IoTs. So in the background all the time, we've just picked some process theory that we're working with. And now we're trying to define something like IoT, starting from it. And the main ingredient is going to be just specifying what the systems are. So they're not just going to be objects in our process theory, they'll have a bit more structure. So you'll end up with this class called sys, and it's going to consist of a load of things that we call system types here. So you just want to say systems. I needed to give it another name. So one of these systems, okay, what is it? So it will be an object of your process theory. And the point is it needs to come with a way that we can think of as valid ways of dividing it up so that we can talk about integration. So that boils down to having a load of decompositions that we've chosen as being like the valid ones that we're thinking about when we're dividing our system up. So it's a set of decompositions, D of this object S. And it's closed under when you can swap the legs of these decompositions. That's not too important. And as well as that, it just needs a time evolution like we had in IoT. So in process theory, this is just some process on our object, and it should be causal. So each specification of the object and what its time evolution is and what ways we're allowed to divide it up is what we would call a system. If we can see how this, we can see now how this gives us something like the picture I had at the beginning for IIT 3.0. If you imagine that your object just came with, we thought of it as being made of elements like we had there. So we have our object, but really we're thinking of it as a big tensor of a load of elements. So like a decomposition, but with more things. Then we could define decompositions to just be partitions of these elements, essentially. So we just tensor a load of them together, and then we tensor the other ones left over together. So that's like this picture at the bottom. We're imagining that S, we're thinking of as just being S1 tensor S2 all the way up to S5. Those would be the elements, those individual objects. And then if you just pick any partition of them, that would be a decomposition. So we could define it, so these are the decompositions. And that's what they do in IIT 3.0. We're just allowing these generalized IITs to just have general decomposition sets, which don't necessarily come from any elements at the bottom. You can just imagine that we want the same kind of thing, but maybe there aren't elements at the bottom because maybe everything's a bit more infinite or something like that. But if you want, you can just have this picture in mind of our systems, that they're just these elements, and the decompositions are just picking out these partitions of them. Okay, so that once we've got this notion of a system, so we've specified a class of these things, we need to be able to talk about the stuff we saw in that picture earlier for IIT. A big part of it is just picking subsystems of your system. So if we've got S and we've got one of these decompositions, so it's C and it's C dash together, then we can turn C into a subsystem itself, which is useful to know, and we're just going to require that our class of systems is closed under this operation. So you can make C a system by, there's a way of restricting the decompositions to C that I haven't bothered explaining here, and there's a way of restricting your time evolution to C that we have in this picture. So remember, the pictures go from bottom to top. So we've got T, right, that's the evolution on S, and all we've done is basically plugged C into it, and then on C dash, we've just used what we know about the state of our system. And we've plugged that in as the input, and then we've just ignored the output at the top. So we've thrown that away. So this is just the naive way we can restrict our evolution to C. Okay, so basically we're just saying that process theories help us do this operation of taking subsystems. So that's useful. The other one was cutting. And again, I'll just say, okay, the language works well for doing this. So you've got your system and you've divided it up as C and C dash. We wanted to make this new cut version, right, that we had on the right of that picture earlier along. So there we were supposed to change the time evolution in some way to make these two parts, C and C dash, not really interact anymore. And there's a way that you can do this. So the simplest way is just to use this picture here, which only looks complicated because I've drawn in all the decompositions as these triangles. But essentially you take S and you just decompose it as C and C dash at the bottom, and then you just let those bits evolve separately, and you just throw away the other part on each side and then plug them back together. So this is now a new time evolution going from bottom to top, where the two halves of the decomposition just wouldn't be interacting anymore. So we could just say that is what cuts are, but to actually capture the cuts that go on in IIT 3.0, unfortunately, those are a bit more complicated. So we're allowing the person specifying the generalized IIT to potentially give a different notion of cuts to this. So this version in the picture here is like the sort of default choice, I'd say. But they might use something fancier. Okay, and the final thing was just to talk about these repertoires, right? So these were the big load of distributions that we obtained from our system before. And now there'll be something more general than distributions. But basically what you need to do is for each system and each one of these pairs of subsystems, M and P, you need to have some processes between them which tell you how they causally constrain each other. That was the idea of these repertoires. So it basically amounts to define a generalized IIT, you give this class of systems, and then you give one process for each M and P of a system, so each subsystems. There should be something called cause, which tells you how M causally affects P, and F to P is how it affects it. So cause is the previous time step, and F is the next one. So a bit more clearly, what you do is you get what you know about M, the mechanism. So you know that it's in some state M, you plug it into this process, cause, okay? And that gives you now, if you look at this picture, cause M, that's a state of P. If we think about the case of classical process theory, a state is a distribution. So this is like the distribution I talked about at the beginning. So this is a distribution over P. It's just telling you how knowing something about M constrains what P could have been in the earlier time step. And similarly for F, it tells you something about the next time step. And yeah, these are called the course effect repertoire values when you've plugged M in. Again, it's sort of up to the theory to say how these are defined. It would be nice to make them a bit more canonical, but there is a sort of obvious choice that you can take. It's just not what's done in IIT 3.0. But the simplest choice for, say, the process F, the effect one, is you just plug in M, ignore everything else, do your time evolution, and then see what's happened on P, and ignore everything else. And you can do the same thing for the cause when your process theory has what's called a dagger, which lets you just flip this upside down, basically. So you'd have T dagger where T is there. So there is a sort of naive way of writing down these repertoire processes, which is still appropriate in a lot of cases. So once you've specified your systems and these things, cause F, you're done. You've now defined a generalized IIT. And later we'll see IIT 3.0 as a special case. And then what you're supposed to do with it is use this algorithm, right, which tells you supposedly something about consciousness. Again, I can only really sketch that here. So what you're doing is you're trying to see which of these repertoire things are the most integrated, like we mentioned earlier. So basically you take each repertoire value, F, plug in a state M. So M is, sorry, so let's just take a step back. So we're starting from our system S, and it's in some state. And now we're applying the algorithm to say something about its experience. What you do in that algorithm, one of the main steps is you look at every subsystem M of your system. So that means every part of a decomposition. And then you also look at every other system again, P, every subsystem. And then you're looking at these values, F from M to P. And you want to see which P makes each one most integrated. And that's what's going on in this calculation here. So we're plugging in what we know about our state at the bottom of F. So what we know about our state is called little m here. And we're saying, okay, how does the state of P that we get out, how does that compare with what we would have got if we hadn't used F, but we'd used what's on the right, which is like a cut up version of our repertoire, right? So we've taken some decomposition of M and some other decomposition of P, and we've just divided this process F over those two. So you look at the minima over all of those because if you imagine that there was some way of cutting it up which didn't change the state, then it's fair to say this thing isn't integrated. So you use a minima, and then you talk about how integrated M as a whole is by taking the maxima over all these P. So anyway, you can do these sort of calculations that you'll see in IIT papers, but using these diagrams instead. And long story short, you end up with this mapping. It takes you from your class of systems into a class of what we called in the other paper experience spaces. So there's just some basic formal objects that capture what you get out of this algorithm. So each system goes to one of these experience spaces, which is supposed to describe all the different conscious experiences it could have. And each state goes to the actual experience that it would have when it's in that state. Yeah, and the details of that probably you can ask me about later if you're interested. Roughly, these experience spaces are just sets with a couple of basic operations. So mainly they just have this intensity. So you can see how intense an experience is. And that's like this big number phi we had earlier. So that's something you can now do. So let's just see what we can actually do with this framework now, right? That's useful. So we want to see how we can make these generalized IITs. So if we start from any process theory that has the features I talked about, and if it had a dagger as well, just so we could do what I talked about earlier with the repertoires, then we can make a generalized IIT now, just by using all the examples I gave as we went. So to give a generalized IIT, we have to tell it what the systems are, what the cuts are, and what the repertoires are. And so I kind of gave examples for each of those as we went. So the systems would be ones defined in terms of elements. The cuts would be the symmetric cut picture I drew, and the repertoires would be the one I drew on the slides earlier. This is the easiest way to define something like IIT starting from a process theory. So we call that theory IIT of C, perhaps a confusing name, but that's what it's called at the moment. Okay, it would be nice if IIT 3.0, so the main one by Tononi and everyone, was like this, because this is a simpler definition. Fortunately, their one's a bit more complicated, so that means they're using some different choices, but it still fits the framework. So it starts from this process theory of classical processes with the metrics that I mentioned earlier. And so it just uses some different versions for how it defines cuts of systems and how it defines these processes F and cause. But you can find them in the paper, basically. I just think it wouldn't be time to go through it all now. But they can still be described nicely with diagrams. And basically what's going on is that this is actually using the fact that it's in not just any process theory, but it's in class. So it's got some classical features around. In particular, it uses copying a lot. So if you look through the definitions of IoT, they use, for their repertoires and so on, they use the ability to copy data. In pictures, that comes out as these spiders. So this white dot we've got on the lower right, that would be a copy map. Just an example of where these copy maps come up. They assume that each time evolution satisfies this condition called conditional independence, which involves the copy, as we can see here. So if you want to see the details of how to describe IoT 3.0, then they're in the paper. What else we can do? Okay, so before we even did this project, Zanardi, Tomko, and Venuti, they defined a quantum version of IoT that they just call quantum integrated information theory. So that might sound a bit complicated. From this perspective, it's actually simpler than normal IoT because it is just defined in terms of this process theory quant. You just plug it in with all our default choices. So it's just this theory IoT of quant. So in that sense, it's actually simpler. It doesn't use anything unique about quant, really. It just uses what you could do in any process theory other than having a dagger. What does that mean precisely? Well, and that means that this is a theory that's a bit like IoT, but now the systems are Hilbert spaces instead, and each one is given as a load of elements tensored together. Time evolutions wouldn't be probabilistic anymore. They'd be completely positive trace preserving maps. And so the states you get out, like instead of repertoires being loads of probability distributions, they're now loads of density matrices. Okay, so that's nice, but it'd be good to do something new, right? So, but now it's clear that we can replace this process theory by something else to build new types of IoT. The first thing you might want to do is just combine this quantum one with the classical one. So the naive way to do that would just be to use our default choices. So do IoT of blah for some process theory blah. And the one you'd use would be C star, finite dimensional C star algebras and completely positive maps, because this is just the obvious thing that generalizes both quantum and classical physical systems. So we could plug that in and we'd get new IoTs. And obviously there's lots of room now for plugging in other types of process theory to get further generalizations of the theory. So just wrapping up, the point of this was to say that process theories are actually, I think, a natural way for studying IoT for those interested in it, because I think they're actually well suited to studying the main notions of the theory. Systems and evolution, obviously, because of these process parts. And I think the fact that they just have this tensor as a primitive operation means they're very well suited for talking about integration, because we saw this notion of decompositions of objects. And it's pretty well known that they're good for talking about causality as well, using these discarding maps, and that's like a big field of study now. So what we did is we defined these generalized IoTs, starting from a process theory. This captured two things that already existed in the literature, the usual version of the theory and the quantum version. And we can now extend to general process theories. And as we said before, even if you're not as convinced about the consciousness connections, this way of talking about integration of systems in process theories could, I think, be of independent interest. Going forward, I think what we would do is want to start changing the theory itself now, probably make it nicer mathematically. So there's lots of ways you could work on changing IoT. Firstly, the notion of integration could perhaps be made more sort of canonical feeling, and it'd be really nice to just study these decompositions a bit further and build up a general theory of integration in monoidal categories in general. These decompositions I mentioned do come with some structure that I just didn't talk about due to time, but it'd be nice to study that a lot further. And then lots of points where we said, oh, you get to choose what the repertoires are, or you choose what the cuts are. It'd be better to make those more canonical, really. So to make the claims of IoT more convincing, I think it'd be better to really have a clear description of how these repertoires should be defined.
We're running out of time.
Yeah, okay. And
so
then
if you want the question, you want or you want to read this?
I can take a question, yeah. Okay.
Okay. Here is a question. Konstantinos says, sorry, I still haven't read the Zanardi paper. Are there observable differences in the values which you can achieve with IIT classical versus IIT quantum?
By values, I guess you mean the phi values or something like this? I mean,
of phi, yes.
Of phi.
Yeah.
I would guess that I'm not completely sure about how you can basically cook up a system to have whatever phi value you want, or at least as big a phi value as you want anyway, even in classical IIT. So it's not really that like quantum IIT lets you get bigger phi values or something like that. So probably, I don't know that it's definitely a theorem that you can get any phi value, but yeah, you probably can get any phi value out of either theory. Then again, okay, quantum IIT is not really understood as well. So it could be that there's something weird about it that means it doesn't actually behave as nicely as you just sort of guessed it would. But they do study it in that paper, so hopefully they say something in there. Probably more interesting is not just the numbers you get out of the theory, though. It's these things that describe experience space and all of that. And the ones in quantum IIT would just be a lot richer because they'd be defined using Hilbert spaces and everything.
Mm.